Thousands of people turn to the internet for help because they have a burning computer and network problem that they cannot solve. If you have a problem, if no one else can help, and if you can find them, maybe you can hire the Packet A-Team.
This is Gary, packetbomb.com. Got another case study for you guys. Simon from an email list contacted me about a Tomcat performance issue that his app team were trying to work through, and they pulled him in to try and solve it. And guess what? Simon did come up with a solution. He did do a solid analysis, saw a problem, came up with a solution, and performance was a ton better. So, but he had some questions, and like, is this normal behavior that we're seeing? Is there a better solution? So I took a look at it, did a shit ton of research and testing on my own to understand it. Still don't understand everything, but did come up with some things. So we're going to go over it. I was able to reproduce Simon's problem because he's in Germany. There's a lot of back and forth, lots of round trip time to get information. So I used AWS, and I used the same Windows that he had, which is Win 2008 R2, and Tomcat 7042. I did just a default install because I've never used Tomcat, but I got it up and running with a default install, and I was able to reproduce the problem. So this is it. This is my capture of the problem. And, you may or may not notice that Wireshark looks a little different this time. That's because in my troubleshooting, I wanted to see certain information that Wireshark doesn't show me, so I added that functionality to Wireshark and built it from source. I'll go over those changes a little bit later, but it's not as pretty as usual because I don't know how to do all the GTK framework optimizations that the binary package has for Mac. So it's a little ugly. I'm so sorry. Okay, performance issue. Does anyone want to guess at what I'm going to go to first? Anybody? All right, click on a packet from the server. Statistics, TCP stream graph, TCP trace. If you guess that, you get, I don't know. What do you want? Okay, so this is the stream graph that I use in pretty much every damn video. But let me real quickly, for those of you who are new, this is bandwidth. This is throughput. This is bytes over time. Bytes over time. So the slope of the line is throughput, is the bandwidth. And what you want to see is a nice smooth line going up and to the right. And we don't have that. We've got all these motherfucking flat spots that just piss me off, and we want to know what's going on. So what I do is I zoom in to the first packet after a flat spot, and I click on it, and that's going to take me to that point in the file. Click. Sometimes it's really hard to, there. Let's move this out of the way. Let's see what's going on. So this is the first packet after a pause. It's 208 millisecond pause, right? So we want to figure out what is going on here, what this pause is all about. So this comes at all these are acknowledgements. This comes at the end of a string of acknowledgements. And it's really important you guys know how to do TCP sequence number analysis. It's not hard. It's just simple math. But you need to understand what sequence numbers and ACK numbers and stuff are. This sequence number is, let's just look at the last few digits, 6533. What that means is it's acknowledging I have received all the data up to and including 6532, and the next sequence number I expect is 6533. So if I want to find the packet that is acknowledging, then I want to find a packet with a next sequence number of 6533. And if I go up, here it is, because I've added a column of next sequence number. Again, next sequence number is not a TCP header field. It's just a calculation of sequence number plus data length. So this sequence number plus this 1296 equals this one. Okay, so this one is acknowledging that one. If we go back up to this one, 5237, we can look at for the matching next sequence number, and it's the previous packet. What that tells me is this packet is acknowledging a single segment, only this one. Now I have a column here, and this is part of the customization I did, that tells me how many segments that these acknowledgments are acknowledging, and it's a 1. It's a single segment, and it's waiting 200 milliseconds. So that's the pattern for all these flat spots. I'm not going to go look at all of them, but I can just tell you that's what it is. So what does that mean? Why would it wait 200 milliseconds? And the answer is this is a delayed ACK. So RFC 1122 requirements for internet host describes when a host should send an ACK. And in here it talks about it should not send it, for efficiency reasons. Let's not send an ACK for every damn segment. Let's receive a segment. Let's wait a period of time to see if we get another one. And if we get another one, then we'll ACK. But if we don't, let's wait up to, say, 500 milliseconds. And if we don't get one, then we'll ACK, right? Let me show you a quick demo. So let's say we got host A, want to send some data to host B, 3,420 bytes. Yeah. Now the maximum segment size that host B will accept is 1,460 bytes. That's communicated in a 3-way handshake. So host A sends the first packet with 1,460 bytes. When host B receives it, it doesn't ACK immediately. It starts a delayed ACK timer, and it waits. Now, host A can go right ahead and send the next packet. And when it does, and host B receives it, host B goes, oh, I got my second packet. Let me kill this timer, and I'll send my ACK. Yay. Host A then sends the last bit of data. It's only 500 bytes this time because we're only sending, 3,420 bytes. So it sends the last bit of data it has to send. There's no more packets coming. When it arrives at host B starts a delayed ACK timer. It waits for another packet, which ain't coming. Now, a typical delayed ACK timer might be 200 milliseconds, so it waits that long. When it expires, it sends the ACK. That's a delayed ACK. So we're seeing lots of delayed ACKs in this trace. And if they're 200 milliseconds each, that's what? 5 of them will equal 1 second. So we're talking a significant amount of time due to the delayed ACKs. So this is what Simon saw. He's like, this looks like a delayed ACK. There's a registry setting in Windows that you can disable delayed ACKs. It's called TCP ACK frequency. You can Google that shit. And you can disable delayed ACKs. And he did, and the problem was tons better, much better throughput, like 10x better, something like that. Now, what are the repercussions of doing that? Well, we're going to have a lot more ACKs on the wire. That's more processing for the host that has to send them. That's more processing for the host that has to receive them. That's more processing for any intermediate device between the two hosts. If your solution is to do this for your entire environment, if you have hundreds of clients or thousands of clients that might be speaking to the Tomcat, this is a global change on the box. So it actually even doesn't matter. If they speak to the Tomcat server, then for every other host they talk to, they're going to be sending an ACK for every single packet. It's not ideal. It's not ideal. It works, but it's not ideal. So Simon's question to me was, is there another solution on the Tomcat side? And also, if you look at this, why would Tomcat send, this is bytes in flight, 64K, wait for all of it to be acknowledged, over 200 milliseconds before it sends any more data? Why would it do that? Well, clearly in this behavior, Windows is treating the 64K chunk of data as an atomic unit, atomic chunk in memory. It's unable to, as it receives all these other acknowledgments up here. Normally TCP would receive acknowledgement and it could purge it from the buffer, freeing up more space. In this case, and I don't know the details of inside Windows of what this mechanism is. clearly it's unable to break the 64K up and remove pieces of it. It's having to wait until all of it is acknowledged before it can flush it from the buffer and send more data. Now, how did he know that it was 64K? So you can, definitely see, you can add bytes in flight, which I recommend you do when you're looking at TCP stuff. And we can see that it's hitting this, 64K boundary before the ACKs start rolling in. If we scroll down, same thing here. We scroll down. So over and over again, it's sending 64K chunks of data and then waiting for it all to be acknowledged. So when I looked at this, my question was, okay, so we've got these delayed ACKs, and I understand what a delayed ACK is, so it makes sense. My question is, if we're sending 64K of data, if the MSS is 1460, then we're looking at 33 packets to get all the data on the wire. So it's always odd. And if TCP normally acts every other packet, it's always going to have that one at the end. But this doesn't happen every time. Clearly, you can see places, lots of places where we have long stretches of data. So it's not happening every time. It's only happening sometimes. And so if we look at the ACKs, it clearly isn't doing every other packet. It's doing, here's one where it does every other packet, because the number of acknowledgements for this is 2, but then 9, 13, 2, 19. What? So we can't rely on it doing every other packet. These are called, when TCP acknowledges more than 2 packets, it's called a stretch ACK. There's different reasons of why it can happen. None of the reasons that I'm aware of are in play here. I think it has something to do with just a low latency environment. We're talking, microseconds round trip time. So since these numbers aren't consistent, if we go down to the next chunk, the numbers change. So the number of ACKs it takes to acknowledge a 64K is different almost every time, or it can be different. So there's no guarantee there will always be 1 on the end. However, when we do have 1 on the end, let me see if I can show you. So you can use, well, you can't because this is my customization. But so these are all the times when there's only a single segment being acknowledged. Now the orange ones are when the delay is a delayed ACK. And you can see there's lots of them, but not every time. I cannot tell you why that happens. Why sometimes it does and sometimes it doesn't. What I can tell you is the conditions and when it does at all. And that is when it's Windows, receiver and sender. So this is only when I tested Linux, I never saw this. But if it's Windows receiving and the data boundary is 64K, that's when it happens. If you change the buffer size to be less or greater than 64K, the problem disappears. Even when there's the same behavior of a single packet, we never hit the delayed ACK. Or if we do, it happens rarely. So that's a mystery. I don't know. You figure it out. So the colors I mentioned, I did orange for delayed ACK. The other one I did was blue for push flag. I disabled a bunch of other junk that that's on by default because I just don't want it on. So I did orange for delta time greater than 190 milliseconds, and if a push flag is set it blue. The other thing I added was I was trying to figure out the buffer size. In this particular capture, it's pretty easy to see. Let me clear this. It's 64K, and we can see that every time it pauses is 64K. The bytes in flight stop at 64K. You can't always go by bytes in flight to give you the buffer size or matching up with a push flag. The push flag is a data boundary of, the send buffer is been flushed completely, or all the data the application wanted to write has been written. So this is an indication, not always 100%, but a good indication of, especially during bulk transfer, if it's, the application is not sending a big chunk of data at once to fill up the buffer it's not a good indication. But if it's bulk data, the push flag is a good indication of the buffer size, the send buffer size on the sending host. So you can't always rely in bytes in flight to tell you that, because that changes once ACKs roll in. If you look at the beginning of this capture, you can see that bytes in flight, doesn't build up all the way to 65K. So when I get to this push flag, the bytes in flight is 8596. Well, what size is the buffer? So I added another thing. This column here that I added is to tell me how much data has been sent since the last push flag. So I can see here that when this push flag was set, we have sent 64K. So that gives me a better indication of, and here again you can see how bytes in flight change, but my column, the push flag is set at 64K. So that was, easier way for me to find out buffer size. So my testing, I played around with Tomcat, and there are some socket buffer settings. So I sent these to Simon. He did some testing, and sure enough, he got the throughput you would expect by setting these higher. And you've got blocking and non-blocking I/O implementations in Tomcat. Simon was able to use these with blocking. For whatever reason, I could only get them to take effect if I use non-blocking. I think details in Tomcat are probably beyond the scope of this. But here's the test I did when I set the buffer higher. If we do a quick, so I want to know right away, do I have delayed ACKs in this? That's what I want to know. So if I sort by my delta column, which is, I'm using delta for time, this delta column actually has a Wireshark bug. And I go down the bottom, I see 35 milliseconds is the highest one. Nothing close to a delayed ACK time. And these are TCP window updates. Window updates are when the receiving host has processed a bunch of data in its receive buffer and cleared some space. So it makes sense that there might be a little delay before you see a window update. No delayed ACKs here. What does our buffer look like? Well, if we go scroll down looking for the push flag, it's around 128K. The bytes in flight are going much higher as well. And we don't have the issue. There's no delayed ACKs. I can look again to see if we have. So we have plenty of times when there's a single segment acknowledged, but for whatever reason, it doesn't do a delayed ACK. And so I don't know why it only seems to trigger that when you're using 64K buffers or data boundaries. So the solution here, I think probably a better way to go is for his application team to modify the configuration on Tomcat to increase the buffer size and not change every host to disable delayed ACK. Now, if you want to be a total stud, I will put this one up, the one with all the delayed ACKs. If you can figure out why sometimes it does delayed ACK and sometimes it doesn't, man, I'll be impressed. You tell me. Please tell me. If you want to be involved with a case study in the future and work with me on a problem, please join the email list. Reach out to me. I hope this real world type stuff is useful to you. I spent a ton of time on this. I've learned a lot in the process of testing and reproducing and researching. And this is an important point. Going from point A to point B, from problem to solution, is not where you get better. That's not how you gain skills and knowledge and get better at this stuff. It's the time you spend in between researching, going down dead ends, getting sidetracked on some similar issue, side problem, tangent. Do those. Follow those. That's where you learn. That's where you expand your knowledge much quicker than if you're just going from point A to point B. So dive in, get dirty, all that stuff. All right, guys. Talk to you next time.